problem.
Okay, yeah, easy. Oh, did you do it, Christos?
Yeah, I did it.
Okay,
It
cool.
seems to be working.
Alrighty. So everyone's got it. Everyone's got it open. I guess first thing I'll say is if you fall behind or like get stuck on something, please yell out because I can't tell, and we're going to be moving at a reasonable pace. So if you do get stuck, don't feel ashamed because almost everyone here is going to get stuck at some point. All right. So you should have something that looks vaguely like this. And the first thing we're going to do is start a new project. So if you go File, New Project, it'll come up with this pop-up. And you can see on the left-hand side, there's 3 locations: local projects, version control, and Monash Nova Rover. If you don't have Monash Nova Rover here, it's because, actually, does everyone have that? Or is some of you missing that? Okay, cool. So we're going to be, essentially, Monash Nova Rover here is the Altium 365. It's like the Google Drive for PCBs. And we're going to put our projects there. So just name it like Altium Workshop and put your own name in the title as well. Something like that. And then, yeah, and you can leave the rest of this and just hit create. So it'll take a little minute. And you can see now I've got a few other projects open, but here I've got Altium Workshop will.project, and there's currently no documents in it. Everyone get that okay? Cool. All right, so step 1 is adding, so like we did in the pre-reading, so the first thing we're doing is the schematics. So we'll add a new schematic. So if you right click on this, you need to right click and go add new schematic, or you can go File, New Schematic. Either or, it's exactly the same. Just make sure you've got this project selected so that it adds to the right project. And bam, we've got our first project. So we'll start with the microcontroller one. So this is for the actual pick. First thing you're gonna want to do is just Control S and save it as something. I'm just going to call it microcontroller. And so this is the schematic for the microcontroller. We're going to be using something called subsheets, which subsheets are kind of like a function in like in programming. So it lets you sort of define your inputs and outputs for part of a schematic, and then you can just use that block somewhere else in your schematic and repeat it if you want to. So let me save. Sorry, 1 second. All right, and I'll close that. Okay, so one thing I've done, because essentially the actual PIC microcontroller circuit with its capacitors and stuff, it's exactly the same between all the boards. So what we're actually going to do is just copy that from an existing project. So if you go File, Open. Nope, not File, Open. Hang on.
Open
There we
project.
go. File, Open project. Yes, that's what I wanted. Thank you. Okay. Yep. And it's the first one here for me. It's called 3v3 PIC template. And if you just open that, you should get, it might have to download, but you should get another project on the left-hand side here with a schematic called microcontroller. Everyone following? Cool. All right, awesome. So all we're going to do here is just Control A to select everything, Control C to copy it, and then go back to your other blank sheet and click on your sheet to make sure you've got it selected, and then paste it. And that's the PIC. So basically this has all of the supporting capacitors and stuff that the PIC requires to operate, the resistors and the programming connector, as well as the crystal oscillator. So this just makes your life easy. You don't have to search through parts and find all this. These are all exactly the same parts that we already have in stock.
Are we missing a couple grounds on the VSS and AVSS?
Yeah. Yes, good point. Okay, good catch. So you can either just click this ground and copy and paste it and stick it on the net there, or you can go this little toolbar at the top. This symbol here is the ground symbol. If you right click, it'll give you more options for other power symbols, but we just need the ground. Cool. All right, so save that and you can close the other schematic and you can actually close the project. So you can right click and go close project on the template because we don't need it anymore. All right, so that's step one. Anyone stuck anywhere before we move on? Great. Okay, cool. So next up, we'll do what do we want to do next? Let's have a look. Probably the linear regulator, I think. So here we'll actually be building. Actually, I'll do I'll do the linear reg. So again, add a new schematic. Again, it's blank. And this time we'll build the entire circuit from scratch. It's fairly simple though. So if you look on Nuclino, there's the page for the linear regulator. The part number is, I don't have the actual part number. Hang on. I'll check it in the chat. Okay, so that's the part number. So the way you do this, so on the right-hand side, you should hopefully have 3 tabs down the bottom here: components, manufacturer, part search, and properties. We're going to need, I think components. Let me check.
Those might also be on the right-hand side along the side of your
or
your screen.
If you don't see them, if you click panels down the very bottom right, they should have a list. Now, I'll just explain briefly what the difference between manufacturer, part search, and components is. So this is where you look for your components to put in your project. Manufacturer part search is it's tied into a library called Octopart, which is like a global library of all components. So if we paste that part number in here, you can see this is exactly what we want. So we can just place that from manufacturer part search. This is like a global library. So everyone who uses Altium has access to this library. The components library is actually our own library within Altium 365. So this is a private library. So this linear regulator isn't in our library. We can put it in there if we wanted to. And sometimes we'll create components for this library that we don't that don't exist. So if you go to manufacturer part search and paste that part number in, it should come up. And you can see there's a bit of information here, even like supply information and how much they cost and stuff in whatever that currency is, whatever. So
Senegalese dollars.
Anyway,
Singapore dollar.
now the most important thing is that so this little green component symbol here, that means that the component in the manufacturer part search has a footprint and a schematic symbol. So schematic symbol is hang on, I'll show you, is just like the symbol on the schematic, what it looks like. So this thing. And the footprint is like the physical pads that are on the PCB, and they're obviously deeply connected. If the part you're looking for doesn't have one of these symbols, you've got 2 options. You can pick a different part that does, or you can make the footprint and schematic symbol yourself. I hope we'll have time to show you how to do that. It is one of the most important things in Altium. We might run a little bit over time with that part. Anyway, so if you can either right click and go place, or you can and just wait for it. You might have to wait a little bit for it to download everything, or you can like click and drag from there, and it'll put them in for you.
Sorry, Will, how did you get the part number?
It's in the chat.
Oh, okay.
Sorry. Yeah, part number's in the chat.
And one more thing with the manufacturer part number search, you might sometimes see that the bar is green, but there's no little component, like no little bug there. That means that it has information about the part, like its specifications and a description, but it doesn't have a footprint.
Yep. All right, cool. So that's the linear regulator. Now there's some supporting circuitry that we need, a couple of capacitors for the linear reg. So there's the input voltage. On the input voltage line, there's a 100 nanofarad capacitor, and on the output, there's a 10 microfarad capacitor. So I'm going to show you briefly how to use one of the most important tools called Octopart. And this is a fairly basic search to start with, but just how to pick a capacitor.
Just quickly, Will.
Yes.
Is there a way to find the data sheet from the component in the schematic?
Yeah. So there's sort of a couple different ways. Honestly, the easiest way is just to paste the part number into Octopart and then just get it from there. You can.
If you click on it, it should have it for most of the ones. If you double click on it, down the bottom, keep scrolling.
Oh yeah, awesome.
Keep scrolling. There you go, data sheet.
Yeah, data sheet. Yeah, so you can do that. Yeah, I'm just a man of habit with Octopart.
Okay.
Cool. So first off, we need a 100 nanofarad capacitor. Now this will sort of the one thing I'm not going to be really able to teach you in this workshop is like actual electronics design. That'll just come with time and practice. But when you're sizing a capacitor, really the two things you need to know are the voltage that it needs to be able to handle and the capacitance. So in this case, 100 nanofarads, and our input voltage is 5 volts, and you'll probably want to size it above that. So if we go to Octopart, so it's just octopart.com, you can just Google Octopart. And you'll want to pick, so capacitors are a passive component. Active components are just like ICs and stuff like that. And like a resistor and a capacitor, they're all passive components. So when you click passive components, you'll see all of these. Obviously, we want a capacitor, so we'll just click that. And if you want to, you can pick a type of capacitor. Doesn't really matter for us right now. A linear regulator isn't particularly fussed about that sort of stuff. So if you scroll down, you can see there's all of the filters for what you want. So if you click capacitance, and you can scroll through all of these. So what did we want? We want 100 nanofarads. So you can click 100 nanofarads. You might also see this as 0.1 microfarads or UF. There's a couple of different things. All right, and here we go. So there's a nice memorable part number there. So there's a couple of other things. So we'll pick voltage. Actually, I won't worry with voltage because you can see all of these are rated to 50 volts, which is well above 25 volts, which is well above the 5 volts we'll ever experience. So these will be fine. The only other thing is the package size. So I know all these pictures look exactly the same, but this one here is an 0805 capacitor, which is 0.8. What is it? 80 imperial mils by 50 imperial mils, 800, I don't know, whatever it is. Yeah. Now we typically use 0603. So this next one here is 0603. There's no real problem with using it 0805. It'll just be slightly bigger. So what you're going to want to do is just copy that part number and jump back into Altium and paste that into the manufacturer part search. And we hope that it has a thing. It does have a thing. So it's got the symbol, which is great. And just double check that the part number that has searched is the right one. Sometimes they'll be slightly different. These are basically exactly the same thing, so it's not a big deal. So same thing.
That might be a good one to get from our library though, Will, because we'll already have a 0.1 mic somewhere.
True. Yeah. So the other option is you can go into the search of our components. You can just search 0.1 mic 0603. And Altium have these. So there's this one, which is the one that will be stocking basically. So we're going to probably have thousands of these. These capacitors are super cheap. You buy 1,000 for like $50. So yeah, so we'll place that, and you'll see here's our little capacitor. So it's a ceramic capacitor, so the polarity doesn't matter, which is why it looks symmetric. Yeah, if it was like an electrolytic capacitor where it's polarized, you have to have one side positive, one side negative, then you'd hope there'd be a different symbol. Sometimes they're not, so just be a little bit careful. All right, so we're gonna how do we connect these together? So you can click on this, place wire, and that'll give you a little crosshair, and you can click between the 2 points. A good habit to get into is Control W. Whoops. Control W is the wire tool. You'll be using this for like always, so it's a good habit to get into using that. And then we need our ground on the other end of the capacitor. Now, one thing I like to do, you don't have to do it, but you can see these pin numbers on the capacitor. Personally, I find them kind of redundant because it's only a capacitor. If you want to hide some of the information, if you click on the capacitor and go properties in the bottom right, you can see all the information here. So if I wanted the part number on there, I could make this visible by clicking the little I. And you can go up to pins here and you can just hide the pin numbers. That's just a personal preference thing. You don't have to do it. But yeah, okay. So we've got the input capacitor. Now we need the output capacitor. So what do we need here? A 10 microfarad. So we might find that 10 mic might be a different size. So we'll uncheck the 100 nanofarad and check 10 microfarad. A tantalum. I believe this is in our library. Where is it? Okay, so yeah, nice. So this is a good example. So this is a tantalum capacitor. These are sort of similar to electrolytics. You tend to use them in the same place, but they're a lot smaller. So this is an electrolytic capacitor, the like kind of cylinder-shaped ones. So I'll chuck that part number in the chat just to save you from searching. And paste that in your manufacturer part search and place it down. Okay, so now this one is polarized. So we've got a positive and negative side, and we've also got the part number here. So what I like to do generally is hide the part number because I don't really care, and then unhide the capacitance. And that way I know it's 10 microfarad. So the capacitance is, again, in properties, and then there's all these parameters down here. Sometimes when you get a part, it might not have these values populated. You can go add parameter if you want to add that in yourself. And again, I'm going to hide the pins just because I like to.
Well, did you say that this was in our component library?
It's not. It's in the manufacturer part search.
Okay.
There will be a 10 mic tantalum somewhere in the component library.
Yeah, this will do.
I guess I only find a 10 mic ceramic. So yeah.
I guess in general, just with like part selection, make sure. So we order almost all of our components through this website, Element 14. When you're searching for components, it's really important that they're in stock at Element 14. So for example, this capacitor is, they've got 22,000 just sitting there. Sometimes Element 14 will appear on this list, but they will have zero stock. It can be easier, instead of searching through Octopart, to just search directly on the Element 14 website, depending on what you're looking for. But yeah, things like capacitors, it's fairly easy to find stuff that will be available at Element 14. When you get into like really specific ICs and stuff that do niche things, it can be a bit of a challenge. Alrighty, so here we'll just connect the two the V-outs together and connect it to the capacitor. And then we'll connect the capacitor negative terminal to ground. And we'll also connect the ground tap of the linear regulator to ground. All right, so that's the whole linear regulator. Now, we've defined so we've like laid out what the linear regulator does. We still need to define like the power inputs and power outputs. So there's a few different options of how you can do this. There's the bar power terminal. There's a circular one. You can use either. Try to be consistent just for aesthetics case. For this one, I'm going to use the bar one. You'll see it says ground, which is a bit weird. If you double click it, you can change the name. So here we're going to change this to be 5 volt. And we're just going to connect this to the input. Now, so whenever you place this symbol somewhere, it will connect that wire to 5 volts. Even though there's no physical wire connection on your schematic, they'll be connected. So there's a few different tricks. So you go.
So do you know if it's case sensitive?
I believe it is, yes.
Cool.
Sorry, I just missed how you got that bar
symbol.
Yep.
So right click on the ground symbol or here, and there'll be a bunch of options. So in general, this toolbar, there's like one symbol there, but if you right click, there's a bunch of extra things that will come in handy. So right click and then either just the blank bar, or you can use the +5 and just rename it. So we'll do the exact same thing, but for the output. So this is a 3.3 volt linear reg. So a standard convention is just to say 3B3. Alrighty. Now we'll save this as the top sheet. So I'm just going to call it top sheet. And this is because all of our subsheets are going to be here. All right, so that's the power, which is great. Now these actually I'll explain that later. Okay, so we're going to jump back to the microcontroller, and we're going to connect up our communication lines that we need. So if you have a look back at the microcontroller, so the blue lines, these PEG and the M clear, they're all connected already to the programming connector, so that's fine. And the oscillator is already connected to the crystal, so we don't have to do that. The first two we need are the I2C lines. So this ASDA and this ASCL. Now we're going to use this thing called a port. So it's this symbol here. And you can just click, and when you click once, it'll place one end, and then you can like make it longer and shorter. And if you click again, it'll place the other end. So this is the SCL. So we're just going to call this SCL. And then I'll copy that and call the other one SDA. So SCL and SDA, they're just the nets for I2C communication. Now, one thing you'll see, these are rectangles, and they've got red squiggly lines on them. This is because this pin here is a bidirectional pin, so signals can go in and out of this pin. But the port here, the I/O, is unspecified currently. So because it's a bidirectional pin, let's change it to bidirectional, and now the lines have disappeared. Well, these ones have, these ones haven't. That should fix itself later. All right. Everyone's still following along? Let me know if you're falling behind. All gravy? Cool.
How did you do the bidirectional pin, that one there?
Yep. So double click on the port, and then it'll jump you to the properties tab, and then you can change I/O type to bidirectional.
Perfect. Thank you.
All good. Great question. All right. So these ports are essentially names that we can reference on other sheets, or we can reference with a thing called a subsheet. So let's go back to our top sheet. And this green little rectangle here is called a sheet symbol. And we're going to place one of these down. So right now it's just a blank green rectangle. So what you want to do is double click it, and actually wait. Yeah, double click it, and then here. So where it says source, file name, it currently just says file name. Click the three dots, and then pick the microcontroller sheet. So now this is a microcontroller, and just give it a designator that's called like pick or something. Doesn't really matter. So now now this green square is linked to our microcontroller sheet. So if you right click on this and then go, I'll show you how to do this twice. So sheet symbol actions, synchronize sheet entries and ports. And then you select both of these and go add sheet entries. Now we have our I2C lines coming out of this. So I'll show you how to do that again. So right click, sheet symbol actions, synchronize sheet entries and ports. Select both of them and then go add sheet entries.
You do a similar thing with the off-sheet connectors. And you right click port up the top. Is that what they are?
These ones.
If you click like the port button, the right click it, does that automatically make it an off-sheet? Like
this is a different thing. We don't really use these. I think you can.
So that's so what we're doing here is called multi-level, like multi-hierarchy design or something. Yep. So basically there's like a top sheet where you connect other sheets like their block diagrams. You can also do like a flat hierarchy where you just have a bunch of sheets, and then anything you need to connect between them, you use an off-sheet connector. If you put the same name off-sheet connector on both sheets, it'll link those nets together. Yep. So it lets you do like a flat hierarchy, but we usually tend to go for the block diagrammy approach because it ends up being much more readable as to where your signals are going.
Yep. Cool. So this is essentially like a function in programming. So we've defined our inputs. In a minute, we'll define our like the CAN inputs as well. And what this means is it's much easier to actually understand what's going on. Like you don't need to care about all the capacitors and the crystal oscillator that's actually in here. All you care about is the I2C lines come out. Excellent. That's great. We'll jump back into here again, and we'll just add so for the CCS sensor, we need this GPIO pin as well.
Sorry, how do you add the SASCL thing
here?
again? No, the micro.
Yeah, for the top sheet.
Yeah, the top sheet.
Yep. So I'll just delete them. So right-click sheet symbol actions.
Oh, yeah.
And then synchronize sheet entries and ports.
Oh, and then select both of them.
And then select both, and then go add sheet entries.
Yep, cool. Thank you.
And then they're there. Cool. Yeah, please interrupt me if you miss something like that, because it's really important and it'll mess you up for the rest of it. Cool. So now we have those inputs defined. We'll jump back to the microcontroller, and let's just we'll use RB7 for so RB are the general register pins. So I'm just going to copy this, and we'll just call it like GPIO1 or something. Now this is giving you a red squiggly line because it's not synchronized to the top sheet. So what we need to do, because we've got, whoops, wrong one. Because we've got three pins in 3 ports on the microcontroller sheet, but only 2 on here. Again, we need to right click, sheet symbol action, synchronize, and then add the sheet entry. You can just manually add sheet entries like this and then name them, but it's it's not worth doing. It just takes too long, and you'll make a typo, and that won't link properly. Okay, so that's the sensor side, and now we'll jump back in again, and we'll add the CAN side. Let me just double check which pins I used. 10, 11, 12. Cool. All right, so we'll just copy this. One thing with Altium, it's the drag to select thing is exactly the same as in SolidWorks. So it might be a bit hard to see, but if you drag from left to right, the square will be blue, and it will only select what's inside what's completely inside the square. If you drag from right to left, the square will be green, and anything that this square touches at all will be selected. So even though I only just barely touched this wire, it's selected compared to the blue. So that can be handy when you're trying to select stuff. So I'm going to select these 3, and I'll just copy them. And we're going to name this one CAN TX. So CAN underscore TX, CAN underscore RX, and CAN wake. You can see the text kind of a bit weird, so we'll just resize these so it fits properly. And then we'll just connect these up. Now TX means transmit, so we're going to make this an output. So it's an output from this sheet. So the chip transmits from this sheet, and the CAN RX is an input, so it receives into the sheet. And the wake, I think, is an output as well. All right. So again, right click, sheet symbol, synchronize, and then we'll add these 3 as well. There we go. So a bit out of order, so I'll just fix that up. Cool. All right. At this point, is anyone stuck anywhere? Please, even if it's back at the very beginning of the thing, I want to know. All good? Okay.
With the microcontroller, do you connect the TX, RS, and the wake?
Yep. So
connect
those ports into the actual pins. Yep. All right. Cool. All right. So now it's time. What should we do? CAN transceiver or sensor? Let's do sensor. So again, right click and add new to project schematic. And this is going to be the sensor. So let's have a look in Nuclino. So we want CCS 811. I'll chuck that in the chat. Oops. So if you throw this in manufacturer part search, woohoo, it's got a footprint. We don't have to make it ourselves. So again, right click, place. And there we go. So if you've done the pre-reading, most of these pins we don't actually use, but we'll need to hook it up correctly. So first off, we want to do the I2C lines. So again, exactly the same as the pick. So let's go SCL and SDA, and then we'll just connect those up.
I'm getting a weird. Is there a reason why my ports, when I drop them, would be like the whole screen in width?
When you
Not sure how to.
When you place it, when you click once, it places like the left edge, and then you can extend it to however long you want. When you click again, it should do the right edge. Is that not happening?
It is, yes. Thanks.
Cool. All good. Yeah, it's a bit weird when you first use it. Again, so we'll set these to bidirectional. One thing you can do, if it's the same object, you can just select both, and then IO type bidirectional, and it'll change both of them. Alrighty. And then we'll also set the wake pin. And I called this GPIO 1. And this is now this is an input here.
Since we're doing the sort of hierarchical design, is it better to label this and wake and then
probably
connect them in the top sheet?
It doesn't really, yeah, probably yes. And that way, when you're looking at the microcontroller subsheet, you'll actually know what it does. Yeah. One other thing I'll quickly show you here, the net label function. So if you have if you have a net is just like a wire, right? If you want to be able to label it, it's quite often helpful to have net labels on things so that when you're doing the routing, you actually know what you're looking at. So you can just go right click, add. I might put it on this one. Oops. And then you can call it GPIO1. Generally speaking, you want your net labels to be the same as your port names. They don't have to be, but you might run into problems if you don't. All right, so so back to here. So if we have a look at the pinout, so like I said in the pre-reading, the address pin just changes the I2C address. We don't really care about that for this. N reset is active low and is pulled up by default. So active low means the reset will trigger when it's pulled to ground, but by default it's pulled up, so it's not going to reset, which is good. So we can just leave that. And nint is, oh yeah, basically this is what we care about. One thing that we haven't done is these pull-up resistors. So I2C, actually, Christos or Joe, do you know if the PIC has pull-ups for the I2C bus?
It has integrated pull-ups on pretty much all pins, so I think it will be integrated.
Cool. So yeah, basically, like the way the I2C pins work is they just pull the pin down to ground. So you need a resistor on the line to pull it back up to the logic level. But the PIC has integrated pull-ups, so it should work without. But if you were designing this board, I'd probably put them on anyway, just in case you couldn't get it to work. And then you can place them. You can choose whether to place them or not when you actually put the board together. All right, so back here, we need a 1 microfarad capacitor between VDD and ground, and VDD is 3.3 volts for this chip. So if we go here and we just search go to components and just search 1UF. One thing you can also do is there's all of these generic components. These are just like sort of concepts of what the capacitor is. And at the very end, when you've finished your design, you can link these to a real component when you're done. So here, I'm just going to grab this 0603 25 volt capacitor. And we want this between, where's VCC? I think it might be EP. Oh wait, yeah, EP is exposed pad, which is ground. Bit confusing. Anyway, so VDD is 3.3 volts and EP is ground. So just hook it up like that. And then we're going to want to add in our 3.3 volt power port to the VDD. Cool. And that is most of the sensor. The last trick is, I don't exactly know what this does, but on the pinout, it says pins 4 and 5 must be connected together. So just chuck a wire between those. And then the rest of these pins we don't use, so we don't care about. So just save that. Yeah, go.
Yeah, sorry, I just wanted to check something. When you're grabbing that 3v3 thing, that's just grabbing the VCC thing and naming it 3v3, or
Correct.
Is that
Yep.
special?
So you can just
cool.
double click and you can name it. You can name it power if you want to. Please don't. But yeah, you can name it whatever you like.
Cool.
Power
Thanks.
labels default shared amongst all the sheets?
Yes. So power labels are global.
Okay, cool.
Net labels are local. So if you name this to be SCL, oops. If you got rid of this port and then like labeled another net on another sheet SCL, these would not link.
Yep.
But if you labeled another sheet 3v3, they would link.
Awesome.
You can actually change how that's configured if you want to have net labels be global and stuff. But just generally, I would avoid it because you can have like same nets on different things and it'll connect to and you don't realize.
Yeah.
Should that GPIO pin be bidirectional or?
I think it's fine as input.
Okay.
As in general, if you're not sure, setting it to bidirectional won't have any problems. It's literally just for Altium to know what's what, and it might help you identify a mistake you've made if you've configured it incorrectly. But like if you have this as an input, it's still just a piece of copper between the two pins. There's nothing special about which direction it goes, really. Cool. So save that, and I just call it sensor.schematic.doc. And then we're going to do exactly the same thing. Oops, not. So we'll add a subsheet for this. Now what you can, so I'll set this to be the sensor sheet. So double click and then go source, file name, sensor.schematic.doc. One cool trick with subsheets, Altium's pretty clever. If you just wire from another subsheet to here and you just click, it'll automatically add the port. So if you know that they're the same, you can do that. But you can see here, right, this has got a squiggly line. The reason this has a squiggly line is here GPIO is defined as bidirectional, but on the sensor subsheet, we define it as an input. So Marty's right, I'm just going to change this to bidirectional and that'll fix that problem. And now the sensor is hooked up to the microcontroller. Nice. Any dramas with that so far?
Okay, sorry, I think I'm a bit confused.
Yeah.
The microcontroller only contains the microcontroller. The top sheet only contains the
linear regulator. Yep.
And then we have a new schematic that contains a sensor.
Yes.
Okay. All right.
Yep. Do you need a minute to fix that up?
Possibly.
Yeah, that's right.
The way to think about the multi-sheet design is like a block diagram. So on your top sheet, you're linking all the blocks together. And then in each sheet, you're defining what's inside the blocks.
Yeah. So you can, like, in principle, I could have put the linear reg on its own subsheet as well. But because there's no input or output ports, it's all just global stuff. It would be a subsheet with no ports, which is fine. It'll still work, but it'll be, it's not particularly helpful, I guess. But if you want to kind of hide this away into a subsheet, you can.
So the pick microcontroller green block thing, is that inside the sensor sheet or the top sheet?
The top sheet.
The top sheet, okay.
Yeah. So the top sheet, so it is kind of like functions. So your top sheet's like your main function. So your main like script. And then we've got this microcontroller function that has these inputs and outputs, and your sensor function, which has those inputs. That's sort of the way to picture it.
Yep. All right, cool.
And for example, if you wanted to have two sensors, you could call this sensor 1, and you could copy this and then call it sensor 2. And then you could hook up another GPIO pin, and you could hook up the I2C lines correctly. and now you have two sensors, and you need to change the address, so it'll be a little bit complicated. But in principle, you can do that. So that's the power of subsheets. You can very, very easily duplicate things quickly, which is great. And it also means that once someone's designed like for example, the pick subsheet, you don't need to design it again. You can just copy it. It's a known working product. You can just paste it in, and that subsheet's good to go. The only thing that changes is your IO.
Yep. I think we're good to go now. Thanks.
All good. No worries.
Yeah.
Thanks for letting me know. So the final subsheet is the CAN transceiver. So again, add new to project, schematic. And we'll just name this CAN transceiver. I probably spelled the transceiver wrong. I can never remember if it's I before E or not. No, it's after C, so I guess not. All right. Now, so yeah, here's a bit of information on CAN bus. We're going to use this chip. This chip is actually not available right now because of the global silicon shortage, but it's just what we've used before. It's going to be easier. So it is the MCP 2562. And oops, I typed it 2562. And there it is. So this is sort of a good introduction to packages and different things. Actually would be best not to just search this part number, because you can see that these are different footprints. So this is a DFN footprint, and it's just different like packages. These are much smaller, but a lot harder to kind of deal with. This is the right package, this SOIC package, but it's actually the wrong chip. It's got FDT in it, which isn't correct. So I'm just going to grab the right part number. So we want this one. So if you paste that in, I think it's in manufacturer part search. Yeah, it is, but it doesn't have a footprint. Okay, so instead, paste it in components. And that's because someone on the team has made this footprint or imported it from somewhere. So there's the CAN transceiver. So what a CAN transceiver does is it converts just like simple like 3.3 volt logic into that like differential pair mirrored signal that you saw in the pre-reading. And it also sort of does the transmit receive like handling a little bit. Yep. So basically how this works is we'll have our TX and RX pins on the left-hand side coming from the microcontroller, and then our CAN high and CAN low going out the other side to our connector. So did I put a schematic? No, I didn't. Okay, so let's build this one. So this is what we'll end up with. Oh, it's not CAN wake, it's CAN standby. All right, I'll fix that. Let me close. All right. So first off, we need a 0.1 microfarad capacitor between voltage source and ground. This is just a standard decoupling capacitor. You'll see these everywhere. You'll probably end up placing hundreds of these in your time on the team. So if you just search 0.1 UF 0603 in components, you can get either the generic ones or this one that we already have. I guess keep in mind when you're searching that 0.1 UF is the same as 100 nanofarad, just units and stuff. Sometimes it can be confusing, and especially when you're dealing with really, really small values like this. So I'm going to use the existing one. By the way, to rotate parts, I never said this, spacebar rotates. And if you want to flip stuff, you can press X and that'll flip horizontally. All right. So I'm just going to run that to there. And so it's a bit gross. I might move the designator up there. And then ground. And now the CAN transceiver is 5 volts. This is because the CAN signals are actually 5 volts. Make sure, like when I pasted that when I copied this in, it used to say +5. Oops. Nope. +5. Okay. It used to say +5. Just make sure you're consistent with what you've defined before. So we used 5 volt here before. You can use +5 if you want. You can use +3v3. Just make sure you're consistent. So that's power. Now we need to connect the, say, CAN TX and make that an input. And we also need CAN RX. I'm just going to give myself a bit more space. Alrighty. And let's add the standby port as well. I'm going to put it here, and I'm going to have to rename all the other ports because I got it wrong. All right. Now the other thing is, so this VIO pin, this defines what voltage your microcontroller is communicating with the transceiver at. So you might have a 1.8 volt microcontroller, you might have a 3.3 volt, you might have a 5 volt microcontroller. So this pick here is 3.3 volts. So we need to give it 3v3 on this pin. I'm just gonna stick it like that. And yeah, what was I gonna say? Can't remember. Anyway, doesn't matter. Cool. So that's the inputs. I'm going to change CAN standby to be bidirectional as well. And we're also going to define, you've kind of got two options here. You could put, so this CAN high, CAN low, you could put the connector for this inside this subsheet if you wanted to. That's fine. But generally speaking, I prefer to have sort of blocks with inputs and outputs. So I'm going to put CAN high and CAN low, hook these up and change those to bidirectional. Okay, so that's the CAN transceiver subsheet. Anyone stuck at all?
You need the termination resistor.
Yes, good call. Yeah, so yeah, it's worth checking against this, isn't it? So yeah, CAN bus at the end of the lines, it's like if you imagine like you've got a big, these CAN high and CAN lows go all throughout the rover and they connect to all the motors and stuff. At the very ends of the lines, you need to put a 120 ohm resistor on the ends. So what we do, even though this device might not be the terminating device, we still put we still put a 120 ohm resistor in case you want to place one later. So you can, yeah, basically when you build the PCB, you'll have a footprint for the 120 ohm resistor, and you can choose whether you actually want to solder it on or not when you build it. So we should have a 120 ohm. Can be a bit tricky to search sometimes. If you do 120R, here we go. So 120, if you search 120R into components, there should be this resistor 120R 0603 part, and we can just place that. And then again, Control W is the wire tool, and look it up like that. And if you like, you can hide the pins. And I'm just going to rename that to 120R just to be clear. Cool. Yep, go.
Button to rotate was R. I'm hitting R and it's pulling up like a bill of materials thing.
So space bar is rotate.
Sorry.
That's right. Yeah, I don't know what that is. Anyway.
On that note, did you say X to flip?
Yeah.
Because that just cut it for me.
Not Control X, just X.
Just X.
So if you're holding it, in your hand and you press X, it'll flip. So like if you've got a chip that like is oriented this way and it's just like not right, it's just not going to be nice, you can flip it.
Cheers.
All right. So let's go back to our top sheet and let's just fix this CAN wake to be CAN standby. So STBY. And into the microcontroller as well, CAN standby. All right, And now let's add our CAN subsheet. So again, source your document to be the CAN transceiver, and you can do the same connection trick with the wire tool. However, we're still going to need to synchronize the ports because we need our output ports as well. So you can see when we synchronize, we've got these are, wait, what's happened here? Right, okay, so interesting lesson here. So designators are what's on the green square, and ports, unmatched ports, are what's on your schematic. And anything on the right-hand side here, links, this is where they've paired up a sheet entry with a port and it's matched correctly. Now, the reason that CAN RX here and CAN RX here aren't paired is because here it's defined as an output and here it's defined as an input. So for this, we actually want it to be an input. So I'm going to prefer, so these buttons here, you can prefer the sheet entry version or the sheet entry version or the port version. So if I select RX here and then click the port, it'll move it over here as an input. Except I don't want it as an input.
Will that actually change it in the subsheet as well?
Yes, yeah, it'll fix it. So I've done that and I've done it wrong. So let's change, I'm just going to change it manually here to an output and go back. Yeah. Sorry if this is a little hard to follow. So I actually want it as an output. So I'm going to prefer the sheet entry version. Now it's an output. And it can stand by, I think it's a bidirectional net. I'm not exactly sure. So I'm just going to prefer bidirectional. All right, so now these are all synced correctly. And we've got these unmatched CAN high and CAN low ports, which is exactly what we want. So I'll just add sheet entries for these.
Can you show how to, because I only have it all in unmatched ports. How do you link the two green boxes so it matches?
Yep, so if you select the RX pin on unmatched sheet entry, so let me try and, I'll just try and control Z back to how it was. So if you select RX and RX, see how they're both selected?
I don't have anything on the left. It's empty.
Oh, so then you just click on the one on the right and click add sheet entry.
Yeah.
Oh, okay.
Yeah. So it's just because I already made these, but I did it, but it wasn't correct.
Sorry, which one did we preference?
RX should be an output. So the port. And then standby should be bidirectional. All right, so you should have something that looks like this. It's complaining here because here CAN standby is an output and here it's bidirectional. So I'm just going to change this one to be bidirectional. And then also go into my microcontroller and change it to be bidirectional. I think it's only an output, but it doesn't, yeah, it doesn't really matter. Okay, so yeah, basically in general, whenever you see a red squiggly line, it means there's something I'm not unhappy about. The reason these red squiggly lines are here is because we haven't actually given our component designators yet. So these are all like capacitor question mark and U question mark. We'll do that right at the end. You can do it automatically just to save us time. All right, so we've got our entire thing now. We're just going to add our input and output ports. So first thing we'll want is our, sorry, not ports, but like connectors. So first thing we'll want is some sort of power connector. Basically we need 5 volts. So, and there's no real, you can pretty much pick whatever you want, but we use a connector called an EP 2.5 connector. We have tons of these. If you search EP 2.5, you'll get this like really atrocious part number. It's because you can only buy like knockoffs basically now. It's kind of odd. But if you place this, it'll be the right thing. So J is the designator for a connector. And because power ports are global, we're just going to use our 5 volt name and our ground. And now, so even though there's no physical connection between these two with a wire, they're logically connected in Altium. All right, so that's the EP 2.5. And now we're going to connect connector for the CAN lines. And we're going to use an Ethernet connector because we're cool. So that's the part number for the Ethernet connector that we have. So if you pop that into components, it should come up. And it'll look like this horrible thing. And with the CAN base, this is what we need to do. So to give you a quick outline, we use an Ethernet connector for a lot of the wiring in the Rover, just because it's cheap and has pretty good signal integrity. So pins 1 and 2 are CAN low and CAN high, and then 3 and 4. Basically, we have 2 pairs of different voltages in here as well, and we also have the RS485 bus as well, which we don't use. And then S2 and S1, these are just the sort of the pins for the like shield. So if you picture an Ethernet connector has like a metal surround on it, that just grounds the surround. So if you go here, you just need to connect CAN low to pin 1, CAN high to pin 2. And then your shield pins, I'll just run that around the back and connect it to ground. And also pins 5 and 8 to ground. You don't really have to do that, but it's just anything that's ground should be connected to ground. Now, just as a general rule, if you're deliberately leaving a pin disconnected, it's a good idea to use something called a generic no ERC designator. It's just this little cross. So if you right click on this little information sign, the third one from the right, it's this little cross, and just click one of these on each of your pins. What this does is it tells Altium that this pin is deliberately unconnected and not to raise an error because it's unconnected. It's also good just for your own sake. If you come back to this board like months later and you're like, oh, what are these pins for? Are they meant to be unconnected? If they have a red cross on them, they're meant to be unconnected. So it sort of specifies exactly. And there's also something funny going on with the designator here. So I'm just going to call this J question mark for now. So J is a connector designator. Okay. So that's the schematic. That's everything. I believe, unless I've missed something.
Well, I was wondering,
yes.
with the Ethernet connector, why do
Yes.
pins 1 and 2 have that funny symbol with the 2 triangles?
I think it's because someone made this, like someone in that team made this. So they've just given, because these are the CAN lines, they've given them no symbol. This just means the pin's bidirectional, so it can be out or in.
And the standard for like 1 and 2 being CAN, 5 and 8 being ground, and so on, is that just like a Nova thing?
That's entirely Nova. Yeah. So
Yep.
the thing is weird.
Do we have that written down somewhere?
It is on
release?
Nuclino. Yeah.
Okay.
So the way our standard works is the first 2 pins are CAN. The pairs in Ethernet are a bit weird. So pins 4 and 5 are a pair. Pins 3 and 6 are a pair, and pins 7 and 8 are a pair. That's
and
just
1
how,
and 2.
Yeah, and 1 and 2. So like, I think the way we've got it is that pin 4 is like 5 or like 6 volts or something, and then 5 is its ground. Pin 7 is 12 volts and 8 is its ground, and then pins 3 and 6 are sorry 5. Something like that. Yeah. Okay. Cool. So that's that.
Sorry, what's the part number for the Molex connector?
The Ethernet connector.
No, not the Molex one.
Oh, this one.
Yeah.
So it's EP 2.5. If you just search EP 2.5 in the components tab, it'll come up. It's this BO2B thing. Blame can't remember which manufacturer. Blame Molex.
It's meant to be a TE part, but I guess we're using the Molex knockoff of a TE part.
No, it's not Molex actually. It's JST. JST knock it off.
Ah.
Yeah.
Interesting. I thought usually JST was the one getting them.
Anyway, or maybe I don't know. Maybe EP 2.5 is the knockoff. All right. So that's that. Now the last thing we need to do is fix all of these designators. So it's a really easy thing to do. If you go Tools, Annotation, and then Annotate Schematics. And then basically just make sure all of these are ticked. This just makes it check all of the schematic sheets together.
Sorry, Will. Where do you go to that?
Yep.
I
So
just missed it.
tools, annotation, annotate schematics,
Yep, got it.
and then just make sure all of those are selected. Or you can hit all on and it'll do it as well. And then, so it's got all of the designators listed here. If you hit update changes list, it'll tell you what it's done, and it'll give them all designators here. And then you can click this accept changes, create ECO. So ECO stands for engineering change order. So if you click that, it'll come up with this big thing. And it's basically saying change C question mark to C1, change C question mark to C2. And you can just hit execute changes down in the bottom left, and it'll run through all of those. If you've got all green ticks, that's a good sign. It means it all worked. And now if we close out, everything's been labeled correctly. So our Ethernet connector is now J3, our power connector is J2, our chip is U2. In general, it's a good idea just to have a quick kind of look over everything and make sure it's all kind of labeled in a way that makes sense.
The most common problem with this is some parts won't by default call themselves R question mark. They'll call themselves R star, and then they won't be picked up by the.
I think it can do R star.
It can do R star, but it doesn't always work. I've had it leave the stars behind. I think you have to change your setting or something.
Anyway, so yeah, keep that in mind. Now, before we start the PCB, if you go, so this is our good friends warnings and errors. So if you go project, validate PCB project, this will essentially compile the project and tell you if there's any problems. And it'll pop up with all of these things down here. Most of the time, these warnings and errors aren't a big deal, but you just do need to check them all. So if you double click, you can see the first error I've got is that net U3_2, so device U3 pin 2, contains floating input pins. Now, because this is an input pin, generally you want to tie it high or low so that it's not like floating in between and the chip gets confused. However, I know that this reset pin has a pull-up resistor internally, so it's not a problem. So to get rid of that problem, I'm just going to place one of these generic no ARCs on, and that will mean that it no longer creates an error. So again, to get that, you right click on the third one from the right and click the X, or once you use it once, it should sort of pick it as your most recent.
There'll be a reason no pop-ups coming up if I hit project and then validate.
Yeah, the error list.
In the bottom right, if you click panels and click messages,
Yep,
does it come up?
it's already ticked.
It's already ticked. All right, is it just
untick
like,
and tick again?
is it like super compressed down the bottom or something? Do you see messages down the bottom like that and you just need to pull it up?
It might be. I'll have a look. Thanks.
Okay, let me know how you go. All right, so that's the first error. The next error is net U4 contains output pin and input port objects. Ooh, I've mucked this up, haven't I? Hang on. That's weird. I thought TX.
TX?
TX is an input on the chip. I think that chip's wrong.
I think this is wrong. All right, ignore that error. I think we need to fix our footprint here.
Why don't you show them how you can edit a footprint if you need to change something?
That's a good idea. All right, let's do that. I'll just show you how to do this because if everyone does this, it'll probably like crash the 365 drive or something stupid.
Yeah, don't everyone try and edit it.
Because it's all shared. So I'm gonna grab the part number.
Actually, you can just right click on it.
After you edit, will it update for everyone else as well?
Correct. Yep. So it'll sync to the drive.
There's another way to find the part. Well, if you right click on the part and go part actions, show component, blah, blah, blah in server.
Oh, cool.
And then you can just right click and edit it.
That's a good idea. All right. So you can do that. So right click edit, or if you just search, you can go right click edit.
There's lots of different ways to do the same things a lot of the time.
Yeah. And you'll kind of figure it out. So this is the component editing page or creation page. So you can see, we've got the name and a description and the data sheet and stuff. And then we've got the schematic symbol and the footprint. So often, often the footprint you can kind of copy from something else because they're often the same. And the schematic symbol you might need to make. So I'm just going to go in and edit the schematic symbol and change this pin to be an input and this pin to be an output. All right. In general, if you want to make a component that, like, for example, if your manufacturer part search, you search for the part and it doesn't have a footprint, just paste your part number in your components library and then just go create component. And then it'll pop up with this exact same screen, but these will be blank and you'll need to make them yourself. There's a few.
Hopefully go over that at the end.
Yeah, hopefully if we've got time. Anyway, so I'll save that and now I'll save. So anywhere you see an asterisk, that means it's unsaved. So I'll just save. And now the kind of creation page is saved. And you can see this comes up as like a component in my left pane here. So if I hit save to server, it'll validate, fix, and it's good to put a little description of what you did. It's basically Git if you've used Git.
It literally runs on actual Git.
Literally
have a look.
You can see the .git folder.
Yeah, but there's no merge conflict resolution, so be careful if you've got two people running on the same thing. All right, now, so we've updated the part, but it's still the same here. So what you need to do is right click, and you can all do this now. So if you right click part actions and then update selected from libraries, and then just go finish, it'll give you the engineering change order again, and you just hit execute changes, and now it's correct. And now it's giving me a different error. Love it. So if you want to kind of update your errors, you can just do validate again. Good news is we don't have any errors anymore. We just have warnings. Warnings are generally okay, but again, still worth checking over them. This first one is this pin here, contains IO pin and power pin objects. This is not a problem. Basically, this pin here is a bidirectional pin, and we've given it a power object. Generally, we could fix this as well, but there's a different designator for pins called just power pins. So it would be better to have this labeled as a power pin, but it doesn't change anything. This component is out of date, so you can just, again, like we just did, part actions, update from libraries. It shouldn't be anything major, but sometimes someone has updated the footprint. It's the reason this is happening is because we copied this from a different schematic, so that was an older version. Interestingly, updating this, the symbol has changed and it's actually shortened it. So just reconnect that, and now it's connected. These are all out of date. I'm just going to leave those because it's not a massive issue.
Actually, here's a good opportunity to show something fancy. If you go under Tools, Item Manager, this gives you a list of all your components. It'll let you see what's out of date in the revision state tab. See on the top, revision state. Keep going right. Keep going. No, left a little.
Yeah.
Current settings. Yeah. Sort by that, and then you can right click on those and update to latest revision and generate an ECO and do them all at once without having to actually find where the components are.
Sorry, how do you get to that window?
It is Tools and Item Manager.
It's not happy.
Go on the right-hand side.
Right.
You got to pick one of the footprints.
Yeah.
There you
go. Yeah, don't have to worry too much about this.
And don't worry about all the errors.
It's a bit about that, but that's okay.
It's because it won't change your comments.
So again, validate, and I've got less issues. The last few warnings. So this is net R12 has no driving source. This is fine. Basically, if a port is defined as an input and there's like no output device on that net somewhere, it will give you this warning. But because it's going to a connector, that's obviously okay. And then here we've just got more conflicts with output and bidirectional pins. All three of these you can just ignore. But yeah, basically, once you've got this green info that says compile successful, no errors found, you should be okay. But still check through all your warnings to make sure you haven't missed anything. Okay, now, so save all of your schematics. And one thing probably worth doing now is clicking Save to Server as well. So this will push all of your updates to the Altium 365 project. So if someone else wants to open it up and have a look, it'll be there for them. And you can also work cooperatively on projects reasonably well at the schematic stage, because each person can be working on sort of one schematic sheet. But like I said before, there's no merge conflict resolution with Altium. So if you work on the same sheet and you both make changes at the same time, you have to fight and pick whose changes get to survive. So yeah, that's a bit of fun. Okay, so schematic is finished. Hell yeah. Now it's time for PCBs. So same as before, right click, add new to project, PCB. Ooh. So this will give you this little black square. This is probably the most graphically intensive thing your computer will have to do. By the way, I should have said at the start, if you're not using a mouse, you really should be using a mouse. I would hope no one's using a trackpad still, but sorry if you are. So a couple of things I like to do first when you start. So this is the actual PCB, and this is the origin down here. Now Altium's a bit weird. This is like the fixed origin. This is like the original origin, and you can't move anything to the left of this original origin, but you can move your origin and then move stuff around it. It's a bit weird. Anyway, just to kind of get you familiar, if you press 3 on your keyboard, it will take you to the 3D mode. There's currently nothing to look at, but this is the PCB. If you press 2, you'll go back to schematic mode. And if you press 1, you'll go to the board editor mode. I can't remember exactly what it's called.
Board shape editor or something. Yeah.
In 3D mode, to pan around, right click. To rotate, it's a bit weird. You hold shift and right click. It's unlike every other 3D tool in the world. It's just something you've got to learn. Okay, so first thing we're going to do is move our origin. So if you do Control G, that will open up the Cartesian grid editor. The other option is, actually, is this what I want? No, this is not what I want. So if you go to properties on the right-hand side, this is sort of the properties of your board. And you can, so there's a bunch of information here. One thing you'll want to do first is scroll right to the bottom and change mils to millimeters. Again, like in the pre-reading, imperial mils, it's here to stay, get used to it. But fair warning, everything in your schematic, do not change that from mils. You will get literally thousands of errors if you change it to millimeters. So leave it in mils, but your PCB, you can work in mils if you like, but I prefer to work in millimeters, just because I know what a millimeter is.
You will very likely have to go back and forth, though, depending on what sort of components you're using, because some components, the pitch is in like inches, and some components it's in millimeters.
Yeah. All right. Now, sorry, give me a second. So if you go View, Grids. No, where is Origin? This is something I always forget how to do because you only do it once.
I think it's an edit.
Edit. Yes, thank you. Edit origin and set. And then zoom. So control scroll is zoom, and just make sure you select right on the bottom left corner of your board. You can pick, I think you can pick anywhere, I think, but bottom left is generally what we do. All right.
Why do we need to set the origin?
Because we're about to define the board dimensions and you want it to be on the corner. Right. So just save that. You can save it as just PCB1. It literally doesn't matter. You can call it whatever you like. Because there's no reference, there's no like multi-board stuff, at least at this level. Okay, so we've set our origin. Now we press 1 to put us into board editor. And we go to design and edit board shape. Now, one thing you'll notice is we have sort of, it's kind of messy. You can pick any value. What I would suggest you do is press Control G. Wait, you'll have to go
Just
back to.
G, I think.
You have to go back to 2, and then our grid right now is set to 0.127 millimeters, so 100 imperial mils. Just set this to 1 millimeter for now, and then go back to 1, and go back to design, edit board shape, and now we can only set our board shape in increments of 1 millimeter, which is good. So you can see in the properties tab, there's the board information and board size. See right now we're at a horizontal width of 101 millimeters. So let me just shrink that down 1 more mil. Now it's 100, and the vertical dimension is 100 as well. So we'll just do a 100 by 100 board. You can certainly compress this much smaller if you like, but it's good to sort of start with a board dimension before you get anywhere.
Sorry, how do you change the dimension again?
Yep. So press 1 to go into board layer mode.
Yep.
Design, edit board shape.
Okay. Yep.
And you can also, there's also like redefine board shape where you can like draw a shape.
Don't do that.
But it'll, yeah, just keep it square if you can. Now the other thing you'll want to do right away is put mounting holes on. Mounting holes is something you don't want to forget till the end because you'll almost certainly have to move everything around to fit them in. So the way you do this is right click on this guy. Should they be vias or pads? I don't know. I reckon vias is fine. Yeah, and then so now it's a bit hard to see, but I've got this tiny little via on my cursor. If you press tab, it'll kind of pause what's here so you can move your mouse, and it lets you change the properties over here. So this isn't a real via, it's just a mounting hole. So we're going to set it to be question from Shaf. If you start off with a larger board than needed, can we change it later on? Yes, you can definitely redefine the board later, and you probably will, but it's best to sort of start with the dimension, like a maximum dimension the board can be. So you kind of fit everything in, and then when you're doing the layout, you'll know pretty quickly if it's going to be too big. All right, so
sorry, how did we get here? I was struggling with the board dimensions. Just add the V.
All good. So go back to mode 2.
Yep.
And then right click here and go via, and then just press tab.
Awesome.
And then, so we're just going to change the diameter. So there's 2 dimensions of a via. The diameter is like how big the copper is, and the hole size is how big the hole is. So like this red ring is the diameter, and this gray ring is the hole size. This is a mounting hole, so we're going to set it to, we use M3, and it's a clearance fit. So you'll want bigger than 3 millimeters. So I don't know, 3.4 mils. I'm not a mechanical engineer, but someone else can corroborate. And just sort of place them evenly in the corners. Make sure you do bigger than 3 millimeters because your bolts will not fit in a 3 millimeter hole.
You might also want to change the via size to something at least as big as the hole. Otherwise, I think you get an error later on.
I think
or at least it shits itself. Yeah.
It's all right. It's fine. So you can see now if you go to 3D mode, you've got holes in your board, which is cool. All right. Now the next thing we need to do is importing the design rules. So design rules are essentially specified by the place you get your boards manufactured, and it essentially defines how small a gap you can have between traces, how small holes you can have, all of the like minimum capabilities of our supplier. So let me just send the design rules in the channel. Where is it? Yeah. Okay, so this is not a perfect design rule file. I made it fairly quickly. But if you want to if we go to gelcpcb.com, which is where we get our boards made, you can have a look at the capabilities page, and it'll tell you like what the minimum clearance between 2 holes is and between a pad and the track. and like how thin you can have spacing and all that stuff. And again, they often define it in imperial mils and in millimeters. So get used to both. All right, so download that file and then go design, rules. And you'll get this lovely looking thing. Right click on the design rules in the top left and import rules. And now we need to select all of these. So make sure you've clicked the top one, hold shift and click the very bottom one. So they're all selected and hit OK. And then we need to import the file name. So wherever you downloaded it, import that rule file.
Sorry, what's the file again?
So in the Slack, in the Altium Workshop Slack channel, I've sent it there.
Okay.
I'll run through this again, and then just hit clear rules.
How do you get to import rules?
Yep, I'll do it again. So design rules. Right click on design rules in the top left, import rules.
Yeah, that doesn't give an option for selecting a file though.
It should. So import rules, it'll give you this pop-up.
Yep.
Yep. And then you have to select everything here. So you just click the first one, hold shift, click the bottom one, and hit OK. And then import your file and hit yes to clear existing rules. And then hit apply. All right, did anyone miss any of those steps? Please say now. I'm happy to do it again.
I actually missed how to change the size of the hole, sorry.
Yep, that's fine. So when you have the via, if you press, so if it's like on your mouse, if you press tab, it'll open up the properties pane on the right. And there's the hole size parameter here. You can change that to 3.4. If you've already placed your vias and you want to just change it, you can just double click and change the hole size that way.
Is there an inbuilt mounting hole thing? Can we just tend to use these because you can ground them easier?
Not really. Yeah, I don't know. These actually won't be connected. You can use a pad as well, like a through-hole pad. Yeah, I don't know. It's a bit odd, but yeah, you can just use it. Basically, you're just defining that you want a hole there. Yeah. All right, I'll run through the design rules one more time. So design rules. Right click design rules in the top left, import rules, and then select everything and hit OK. And then find your file and clear existing rules. And then hit apply. Okay, hopefully everyone's got that. If you don't have it, it won't matter too much, but you might have a couple of errors. All right, we're probably going to run a bit over time, so sorry in advance. The next step is, so we've defined how all our components are connected together in our schematic. Now we're going to import these components into the PCB. So if you go design, import changes from Altium Workshop Project PCB. Now the other one, update schematics, will run things in reverse. So any changes you've made to your PCB, it will update your schematics. You never ever use this. So only ever import changes from your schematics into your PCB. So when you click that, it'll give another engineering change order, and it'll just have like add all your components and your nets and your rooms. So hit execute changes. This might take a little second. All right. Now you should have all green ticks. If there's any red crosses, you might have a problem. It'll come up in the messages if there's a problem. All right. So you can see here we've got these 4 kind of red boxes. These are exactly the same as our slip sheets. So this top sheet has the linear regulator stuff and our connectors. This sensor sheet has the sensor and the capacitor. The PIC, the microcontroller sheet, has all those connectors and crystal oscillators, capacitors, and the CAN transceiver has the stuff it needs. So what you can do is you can sort of move these rooms around and then like route, place stuff within those. But I might do it for the pick, but for the other ones, I'll probably just delete the rooms. So you can resize your room to give you a bit of room, no pun intended. And so if you want to like move all of these components together, they're kind of tied to the room, so they'll move as one group. Now you can see all these gray tan colored lines. These correspond one-to-one exactly to those connections that you made in your schematic. So for example, the crystal oscillator here, it's a bit hard to see, but there's a line connecting from this pad to this pad here. So the first thing you do when you're creating a PCB is the layout. It's the most important thing you do. You've got to sort of lay stuff out in a way that makes sense, and there might also be requirements for your layout, like on how close things need to be together in order to kind of get expected functionality.
I just had a question, Will.
Yes.
What are the purpose of rooms? Is it just to like help with layout?
Yeah, so in this case, they're not particularly beneficial because we don't have any repeated rooms, any repeated subsheets. But for example, if you had like 4 or 5 of exactly the same circuit repeated, like say you had a USB hub and you had 4 USB connectors and you had all the supporting circuitry for those connectors, you could have those as subsheets. And then when you route a single one of these, you can then apply that same layout and routing to all of the other rooms, and it'll just copy across. So it saves you a lot of time in that regard. You don't have to do it all manually. But in this case, because we've only got one of each room, there's not a ton of benefit.
Awesome.
The other useful thing you can get out of it is if you route each room, then you can move all the rooms around and find a good layout on your board. So it can be helpful if you want to route each sub block with all its needed components and then wiggle them around to try and find the best spot for them.
All right. So one thing I find quite helpful to do, so for as you're looking at each room, have the schematic sheet open for that room, just to kind of get an idea, because sometimes it can be hard to kind of remember what kind of connects together. So here we can see that C1 and C2 connect with X1, the crystal oscillator.
You can actually put the schematic on your second screen if you have a second screen.
True. So here, I'll move. So this is X1. We've got C2 here and C1 here. And we actually want these laid out roughly how they actually are in the schematic as well. So if we put, so again, spacebar is rotate. And so if I have it in this configuration, see how the lines are crossing? That means I'm going to have to route the lines over each other, which I kind of want to avoid. So you can easily fix that by just rotating at 180. And now you've got your designator. Oops. Your designator is kind of, why is it doing that? Let me turn my grid to, nope. Okay, I'm just going to delete the room. There we go. So the designator is kind of in the way. I just deleted the room because it's not super important. So you can sort of move the designators around as you wish. You can even hide some of the designators if you want. So say, for example, you have like 8.1 microfarad capacitors all in a line. You can hide the designators and then put your own kind of silkscreen explanation of what they are. So I might just replace all of the designators with just a 0.1 UF text. And that all these designators are is to explain to you when you're building your board where the components go. So if you can convey that information in a different way, you can do that. So I'll put that designator there. And then again, oops, let's put this capacitor here. All right. So that's the layout of the oscillator. I might just move it over a little bit. And yeah, so just kind of play around with where they go. Check back at your schematic. So C4 and 5 kind of cross over a few different pins. So C4 is between pin 27 and 28. So which is up there.
Well, it looks like my crystal oscillator is sort of oriented differently to yours. Like C1 goes on, instead of going on the bottom, it goes on the left.
So because see how these are all ground, right? So
Yeah.
that line will give you the shortest line. So if you move it to the side, it will connect. It'll show you the closest connection
right.
to any ground plane pin. I think having you could probably do it like that, and it would probably be fine.
Yeah, I've just
yeah
moved them around, and it's worked now.
Yeah, that's cool. No, good point. One thing that I do like to do in general is because there's so many lines here, especially when you're working with much larger projects, it can be incredibly overwhelming to look at all these lines and to kind of understand where things go. So if you go view connections, you can see there's all these options here. So you can show net, hide net, show all, hide all, show component nets. So one thing I generally do right away is I hide net and I just hide the ground net because that's the ground net we sort of route automatically using something called a ground plane at the very end. So it's not particularly important that you know where they are.
Sorry, could you step through the net hiding?
Yep.
again?
So view connections, hide net, and then just find any ground pin like this one here and just click it, and then it'll hide all the grounds. You can also, if you don't do that, you can just click anywhere and then you can type ground and it'll do the same thing. But it's usually easier just to do it that way.
Also, how do you move designators?
Yep. So you should just be able to click and drag on the designator itself.
If you've still got a room there, it'll often try and move the room instead of moving the designator, though.
Yeah,
that's
so
what I'm getting.
If you've got a problem with that, the alternative, instead of deleting the room, this filter tool is your friend. So if you click on this, it'll show you all of these things, and basically it makes it impossible. So if you unselect rooms, you can no longer click on rooms. They'll still be there, but you can't click them. So that's what I would do in that situation. And now you should be able to select the designators. It's also helpful. You can turn all of them off and do texts, and then you can Control A and it'll select all the designators. So if you want to make them a little bit smaller or something, you can do it that way. Yeah, so that filter tool is really cool. Just remember that you're using it because you might go, why can't I click on any text or something? And it's because you've got it deselected.
Hey, Will, how do you rotate the components?
Yep, so exactly the same as the schematic. So you just click and drag it and then click space and it'll rotate.
Yep, nice, thanks.
Cool.
How close can we put components? You've got the C1 really close to the oscillator there.
Yep. In principle, so in principle, this is fine, right? What I've got here. It's only a problem. Oh, hang on. Oh, I don't think my design rules are good. Uh-oh. Okay, never mind.
I think that part doesn't have a mechanical outline.
Yeah, so basically there's two constraints. One is so if you go to JLC capabilities, the pad-to-pad clearance of two different nets has to be less than 0.127. The reason this is allowed is okay, so there we go. The reason that's no. There we go. The reason you can put them inside like that is because these are the same net. But you can see, and you can see that in the 3D model. Oh yeah, by the way, have a look at the 3D model. You've got all your components. They look cool. You can see that the actual size of the crystal oscillator is slightly smaller. So it's not complaining about a mechanical interference here. But in principle, you should basically not overlap the sort of purple boxes.
Is that just because that component doesn't have a courtyard attached to it?
Pretty much, yep.
Yeah.
So if see that green outline on a lot of the parts, so that's something that should be on most parts, especially if you're going to make them yourself. That's an IPC class, density class courtyard. So there's specific international rules for if you have a medium density board, then you must have this much space from the edge of your pads. So if you don't overlap the green boxes, then you're compliant with whatever IPC density that footprint's been made for. But usually the courtyards are done with the green boxes rather than the actual courtyard layer. I don't know why.
But just to check, so those density limits, is that to restrict the density or to enforce a minimum density?
Restrict,
Okay.
yeah.
But why wouldn't we want to overlap the nets? That seems really convenient.
So for instance, you have to physically assemble this board, right? So the IPC, the highest density is for pick and place assembly and reflow soldering, where you're using a robot that can place it really, really precisely. IPC medium is for hand assembly, reflow soldering, and IPC low is for hand placement and hand soldering, because you actually need to be able to get tweezers around it to get a soldering iron on it, and you don't want things to short.
So there's sort of two restrictions. One is like mechanically these like are colliding, and they'll go green in the 3D model if they're colliding, and they'll also have the green crosses. So if you see green, it's bad, which is really nice of Altium. So red is good, green is bad. The other constraint is so for two different nets, if I just move this designator out of the way, so like this is C12 and C22. If I bring these closer together, you can see this here says less than 0.1 millimeters, and that's the constraint of the pad to pad clearance. I don't think it's defined exactly correctly, but it's it'll do for now. Sorry, someone in the chat. Yeah, so silk screen. So the yellow lines are all silk screen, so it's printed on the top layer. So if you press 3, you can see all of the yellow turns to white, and that's what physically appears on your PCB. All right, so I'll just put these back, and let's just keep doing the layout. So R1 needs to be near pin 1. So that's pin 1 there. One trick you can do as well, alongside the connection lines, if you control click on a pad, it might be a little bit hard to see, but it brightens that pad and dims everything else. So you can see everything that is connected to this net will now be slightly brighter, and it just can make things a bit easier to see. To undo that, you just control click anywhere else, and it will go away. All right, so I'm just going to put that up there. And then R2 sort of connects to R1. I might put that sort of next to it. C5 is between 13 and 19 and 8.
My components are all sort of snapping to that 1 mil grid. How
Yep.
do you turn that off?
So Control G, and then you can just make your grid smaller. I just did 0.01.
Yep.
Some people love grids, some people don't love grids. I don't know. It's sort of
place your
thing.
components on grid. Don't be a savage like Will. 0.1 mil grid is handy for making them look good.
Be a savage like me.
When you're doing traces, though, you can turn the grid as low as you want.
Yeah, just for here, it's not but Control G is always grid.
G also lets you swap between like common grid sizes.
And also, if you like have a snap grid, let's demonstrate. If you have a snap grid on, wait, why didn't it saved to 1 millimeter? If you have a snap grid on, but you want to like not use it temporarily, you can hold Control, and it will sort of disable the snap grid. So that can be handy sometimes. All right, so C5, these aren't like crazy important. I'll put this one in here. Okay, and then C3.
Shrink your designators, Will.
Yeah, okay, I'll show you how to do that. So if you go filter, turn everything off, and then select texts, you can now just Control A, and it will select every designator on the board. And I think the minimum height is like 0.9 or something. So if you change the height, they'll be like kind of chunky. And I think it's 0.15 for the stroke width. So now the
stroke width was something imperial. I can't remember.
Yeah. Anyway, so the designators are just a little bit smaller, so they kind of fit better with those 603 components. So you can rearrange those if you like. And then don't forget to turn on all your selections again, so you can actually move components. Okay, so C3 goes next to pin 20. So that kind of lives over here. Now, one thing you want to do when you're doing a layout is also just consider the physical size of the components you're laying out, and how you're going to be assembling the board. So for example, this pick, it's going to be changing in future, hopefully, but previously we've been hand soldering these picks because they don't survive our Toasty Boy, the reflow oven.
A reflow oven shit.
Yeah, it's not very good. It's all right, but it's not great. So if you're hand soldering this board and you've got this capacitor right next to it like this, you're not going to be able to physically fit your soldering iron tip in here very easily. So
ask us how we know.
Yeah.
The CMD, the single most fabricated board we've ever made, has that exact issue.
Yeah, so it's worth putting a bit of a gap in just to make things easy. And because we've got tons of space here, it's not a big deal. All right. And I'm just going to whack the program connector like up there. All right, so that's the layout of the pick done. If it's not exactly the same, it doesn't matter. Now I'm going to do the sensor. This one, the layout's super simple. It's just a decoupling capacitor next to it like so. All right. And now we'll do the CAN transceiver. This one's also fairly straightforward. So R3 goes between the CAN high and CAN low pins, and C9 is just power decoupling. And then finally, we've got our connectors and the linear regulator. So I'm going to whack the big Ethernet connector down the bottom here. And I'll put power next to it. Why not? So that's just kind of how I want it laid out. And then linear regulator, we've got 3.3, a cap between 3.3 volts and ground. And then another capacitor between 5 volts and ground. I'll probably do. All right, so you can see that's kind of what it looks like. All right, so as you can tell, we definitely don't need the board to be this big. So at this point in time, you could probably start, you could start moving these around and kind of placing things a bit tighter and then shrinking your board down. I'm not going to worry too much at this point, just to save us a bit of time, but just sort of generally lay out your kind of blocks in a way that makes sense. So for example, the CAN transceiver, I'm going to put this so that the CAN pins point down towards the CAN pins on the connector. You can see we've got nice straight lines for this connection here. So in general, if you've got wires that like don't cross over each other too much, you've done your layout pretty well. But you'll often get crossing overs with power lines and stuff because they tend to run everywhere. But yeah, so you might also want to hide your 5 volt and your 3.3 volt when you're doing routing, and I might actually do that now. So
sorry, I've forgotten how to find the grid, like change the grid size.
Yep. So Control G, and then
Control
you can change
G,
it.
right.
Yep. So what I'm going to do is, so same as before, view connections, hide net, and I'm just going to hide the 3.3 volt and the 5 volt nets. And now everything that's here, that every line I can see is a signal line that I have to route. It's generally best to start with signal lines because they are sort of the most fussy. Power lines are pretty chill. Okay, so let's jump over to the pick. And I've noticed something immediately. So with my crystal oscillator, if I route these, so routing, same as placing a wire in the schematic, so Control W, and that brings up this boy, that's Snake Boy. If you want to change the dimensions of your trace, it's the same as the VIA before. So while you're routing, if you press tab, it'll pause, and then you can change the width here. So a typical width is like 0.254 or 100 mils. And that's fine. So immediately I've gone, oh, hang on. If I want to route this wire here, these are going to cross over. And that's not fantastic. So instead, I'm going to flip this over. So if I can select all of those, hit spacebar twice, and I'll just move my designators so they're kind of in the right orientation. And now when I route it, these wires don't cross anymore. So I can do Control W, and that looks all right. Also with crystals, you kind of want to keep the lengths the same length of the traces. It's not overly important, but
I think you're also meant to put like a ground ring around it. There's something in the pick docs about how to route.
Yep, you're meant to put a shielding ring around it, but I think that's a little bit beyond the scope of this.
Yeah, we'll show you how to do a ground plane, which will cover most of it.
No, it's meant to be like a ring around it to, I don't know, shield it from something.
Was there a way before to like select all the power lines and hide them? Or you have to do like hide net for each one?
You do have to do hide net for each one. Yeah.
Okay.
Yeah, there's no, because yeah. There might actually be a way of doing that, but I'm not exactly sure. All right. So that's the crystal hooked up. Now let's do the programming connector. So we've got this wire here. And we've got this one. So you can run traces underneath components. That's fine.
Is there a keep out zone kind of signifier? Or just like if they don't recommend you run any traces under this device, is that made obvious?
I haven't run into any devices that have that.
Okay. Yeah.
But probably not. That would be something in the data sheet that you'd have to check.
Yeah.
All right, and I'll hook up the cap. So I might make, because this is like a power line, I might make it a bit of a slightly fatter trace. And I'm like, whoa, not that fat. 0.5, please. There we go. So 0.5, and that's here we go. So this is a problem. So if I set it to 0.5, the distance between this trace and the edge of the necked pad is less than 0.2 millimeters, which violates JLC's capabilities. So I can't do a 0.5 mil trace here. So I'll have to do something slightly smaller. So I might do like 0.45. And I think that's okay. Nope, it's not okay. All right, maybe 0.4. There we go.
Back to your question, Isaac, there is a keep out layer. I have never seen a footprint use it. Any of the automatically created footprints or anything. But if you do find a component that says you can't route stuff under it, I think you can add a keep out. Just add a box on the keep out layer, and it won't let you route through it depending on your design rules.
Just quickly, CAN doesn't have differential pair requirements to it, does it?
It does technically, but they're not very high. So you can route it as you can set it as a differential pair. We're not going to worry. It's a bit out of the scope for today.
Yeah, it's not worth paying the extra money for impedance controlled PCBs, especially because it's like 1 centimeter stubs when you can do 0.5 meter stubs on CAN. But we do try and route it when we're doing the cables with a differential, like with a twisted pair.
That's fair. I haven't found the cost to be too bad, like a $0.50 extra.
It depends on how many boards you're ordering. If you're only ordering 5, you can get 5 100 by 100 boards for $2 if you don't change any settings.
Alrighty, so just keep trucking along. So I'm now going to hook up the I2C sensor. So just Control W again, and it's literally just connect the dots. So if I route the GPIO pin first, you'll see that it kind of makes my life difficult routing the I2C lines. So I'm gonna undo that, and I'm gonna route the I2C lines first. So you can see they go nicely. Now, how am I gonna get the? So there's sort of 2 options, right? If I wanted to route this connection here, I could route it all the way around the chip and do it like that. That's technically fine. Nothing like it will still work, but it's much easier and neater to use the second layer of our PCB. So right now we've been working on the top layer the whole time. It's time to venture down to the bottom layer. So if you start routing and click and start your route, this is sort of one of the trickiest kind of combos to get your head around. But if you hold Control Shift and scroll up once, it will switch you to the bottom layer, and it'll automatically put a wire in. So now I'm on the bottom layer, which is blue. And then, so I'm going to click once and then do Control Shift and scroll up again. And then, so now I've jumped underneath, physically underneath these. So if I show you, so I've got these wires here, and I can show you the underside of the board. You can see the trace. The trace goes through these wires and to that connection there. So pretty cool.
If you want to move a component, I'm getting that the traces don't, like that they sort of stay and get all broken and mangled.
Yeah, so yeah, if you move
Is
a
there a
component
way to make it
afterwards,
attach?
not really. That's why layout's so important. But that you get it right before you start routing. Don't feel ashamed if you need to reroute something like half a dozen times to get it to go correctly, because you'll route something once and then you go, those traces don't they overlap in a way that I don't want them to. Let me rearrange everything so that it's correct.
Yeah.
But you can select, like if you want to move like a group of components, you can select everything, including the traces, and it'll behave correctly.
Are you using a 2-layer board right now?
Yes.
Just as a note for that, going under the second layer, if you have a high frequency trace, the ground reference is going to be directly underneath it. So if you cut under it, you might end up with some issues. So if your USB lines don't work, it could be that. And you can usually solve it by running a ground trace alongside them for a constant reference.
Yep. So if you're doing really high frequency stuff, you'll typically use a 4-layer board, and the second layer will be entirely ground plane.
Yeah.
And then the third layer will be some voltage reference, and the fourth layer will be your routing. Typically with high speed stuff, we try to avoid routing it through layers at all. But yeah, cool. All right, see you, Michelle. All right.
Just again, how did you drop the routing down to the second layer?
Yep. So start your routing with Control W.
Yep.
And then hold Control Shift and scroll up once with your mouse wheel, and that'll put a via in. And then scroll up again, and you'll jump back.
Perfect. Thank you.
Now these vias here, you can change the size a little bit. The minimum via size that GLC can make is a 0.6 diameter and a 0.4 hole size. So if you're really space constrained, you can shift them down to that. But what we've got here is fine. All right. So we've routed the pick except for the power stuff, but that can come later. Now I'm just looking at these lines here, and I'm going, oh, I'll have to route them all the way around, and it'll be a bit messy. So what I'm going to do instead is I'm going to grab all of this and rotate it 3/4 of a circle. And I might just move, I don't know, let's see, I might just move all of this over to like the middle. One thing as well with your mounting holes, it's probably worth locking them. So if you right click and we'll say like component locked or via locked, if you click that, then it'll become a tick box, and then you can't move it anymore. So it helps when you're like, if you like select it accidentally, you won't move everything around. Alrighty. So we'll jump over to the CAN stuff. So just routing between the CAN high and low through the resistor and to the connection. And what's this net? So this is the CAN wake. So that, oh, sorry, CAN standby. Now I can see a problem here that the CAN high and CAN low, sorry, the TX and RX pins are going to have to cross over at some point. So if I had time, what I would do in this scenario is I would actually go back to my pick, and I would remap the TX and RX pins to be the other way around. Because they're just register pins, I can change those as I please. But in this case, I'm just going to route them underneath each other with a via to sort of save time. So I'll route this one underneath. And then the same for this one. When you're like routing, if you want to like get out of it, so if you've got the green cursor on your mouse, if you hit escape, it'll get rid of that. If you're like midway through routing and you hit escape, it'll cancel your current route, but you'll still have the green cursor. So you'll need to hit escape again to get out of the routing tool. So basically what that means is you can route one thing, hit escape, route another thing, hit escape, and then you can hit escape once you've done all of that. If your like mouse is doing something weird, just like spam escape a couple of times and it'll probably fix any issues you've had. All right. So yeah, this is probably not like the nicest routing of the CAN lines, but it'll do. Okay. Cool. Thanks, Tom, for coming. Alrighty. Now we'll do the linear regulator. Because these are power lines, I might give them a bit fatter traces, maybe like a 1 mil trace. And so because we hid our connections earlier, I'm going to go view connections, show all, and this will show us everything. And then I'm going to hide the ground net because we can do that automatically at the end. So here is the 3.3 volt. And just sort of hook up, we go around and like hook up all your power lines together. A couple here. So like obviously here, a 1 mil trace is way too big. So I'll drop that to like a 0.4 something. That's good. I've also got to connect these nets together. Remember that pins 4 and 5 had to be connected. And then on this chip, the exposed pad on the bottom of the chip is the ground net. I think it was the ground net. Why is that? Actually, let's have a look. That's a problem. All right, so see how this is called C81, and I thought it was ground, but it's not called ground. That means there's a problem somewhere. And I had a look at the schematic, and we actually never hooked up the ground port to this correctly. So we need to add that in. So when you make changes to your schematic, it won't automatically update in your PCB. So you need to do that same import from before. So design import changes. And it's gonna try add all the rooms back. So I usually just disable all of same kind for rooms. Cool, no worries, Marty. And execute that. And now this is ground. And that's also complaining about something. It's complaining about these wires. Okay, don't worry about this problem. This is a problem with the part. But just connect your ground together. Sorry, that was probably a bit fast. Did everyone get that? So you just got to add the ground to your EP pin on the sensor, and then synchronize your changes with import changes. And then
Just missed the part where you disabled the addition of the rooms. How do you do that?
Yep. So import changes, and then so these are all like adding the rooms. So if you right click and go disable all of same kind, it'll just uncheck them all. And then when you execute it, it won't do those. You can, if I do that, what'll happen is it'll put all the rooms here empty, and it will turn everything green because it's not inside its room like it should be. If you accidentally do this, there's a pretty easy fix. Just turn off all the filters except for room, Control A and delete, and it'll just delete all the rooms.
What was that issue you had with the vias under the yeah, that one.
Yeah, I'm not exact. It's a short circuit violation. So that symbol means short circuit. It's because these, I can fix it in the component editor, but these vias, which are like a part of the component, have no assigned net. But the pad is assigned ground. So it's not happy because they're shorting against each other, basically. So you just have to you'd fix this by just, there's a couple of different ways you can do it. I would probably just remove the vias from the footprint and add them in yourself afterwards.
Can we actually solder that ground pad? How would we do that?
So this would be a reflow or a hot air gun.
Oh, true.
Yeah. So yeah, exactly. You're right. You can't hand solder this because you can't get to that pad without being able to break the fourth dimension. All right. So just keep kind of routing together all your connections. Now the PIC program connector also supplies its own 3.3 volt power supply for programming. So we've also got to connect that. And now so we've got a few kind of 3.3 volt lines that we need to connect together. So I'm going to route these kind of on the back layer. So I can just like jump up to the 3.3 volt. And
so I've somehow managed to change the size of my traces to a huge thing. I'm not quite sure.
Yep. So you can either, so while you're routing, just press tab, and then the width on the right hand side here, you can change that. So like 0.4 is reasonable.
So not 10 millimeters.
Yeah, that'll be a little large. All right. So yeah, I think also remember if you're routing on the bottom layer, you can actually route underneath surface mount pads, and there's no problem here because they're not physically connected. So there can be a couple of tricks in routing that way. So those 3.3 volts are connected. See you, Michael. And then finally, this one. Okay, cool. And also this one. So yeah, I guess my take-home message is the schematic is the hard part. Routing is just connecting the dots. And it just takes time. See you, Justin.
Are there any rules in regards to like trace widths and like how much current is flowing through them, or is it?
Yeah, you'll have to do some research on it depending on your application. Obviously, traces are essentially wires, but the thinner they are, the higher their resistance, and also inductance. But that's more of a signal integrity thing. So yeah, if you're running like high current, like 5 or 10 amps through a trace, you're going to need very fat traces. And you might also want to consider one thing with JLC, you can get, there's a thing called copper. So you can see here, there's like 1 ounce or 2 ounce copper. That actually defines how thick the layer of copper is in your PCB. So if you've got a thicker layer of copper, you can pass more current through without it heating up as much. Okay.
How large do you recommend the 5-volt line trace be?
Look, it doesn't have to be overly thick. Like 1 millimeter, if it needs, is fine. It's 0.4. It'll be pretty much anything you can do here will be fine for this application because it's not very high current.
Cool, thanks.
All right, so I now have all of my signal lines and all of my power, like voltage lines hooked up. I just don't have ground hooked up yet. How's everyone going with that? You guys need a bit more time?
Almost there.
Yep. So if you're done, you can suss it out in 3D and have a look. And this is basically what the board will look like. There's no 3D model for this connector, but you can Google it if you want to know what it looks like.
Coming onto some pins on the pick, the like chonky power line intersects with the pins. Just shrink it back down right at the end point.
Yeah,
is there a specific, like a faster way than clicking each trace segment and shrinking it, or does that have to be manual?
So while you're routing it, if I do like a 1 mil section there, if I press tab and change it to 0.4, it'll just change that bit.
Perfect. Thanks.
Yeah.
And I think if you click on a trace and then press tab, it selects the whole net. Yeah.
Oh, I did not know that.
Or the whole connection. So
That's
if you want to shrink everything that you've placed, you can do that.
Nice. There you go. See, you learn something new every day.
Yep.
There's lots of little tips and tricks in this. You'll sort of pick up with time. All right. How's everyone going? Do we need a bit more time? Gemma, do you need more time? I'm going to ask specifically.
Thank you. All good.
You done? Okay, cool. All right. So the last step is the ground plane. So essentially this just fills in the rest of the board with a solid piece of copper that's connected to ground. And this means you don't have to route your ground nets. You can just get this to do it for you. So what you do is this tool up here, place polygon plane. If you click that, it'll give you the green crosshair. And then you just need to, it might help to go back to a 1 millimeter grid. and you just like select the four corners of the board in order. And then it'll give you this sort of red square. But we're not done yet because you can see it's not actually connected to the ground. And that's because in the properties, the net part still says no net. So you can either type in ground here, or you can click the eyedropper and click on a ground net. And then it'll change this, but now it's gone this like green. It's gone all green and it's like, what the hell's going on? It's because it's not poured. So when you do a change, it will unpour the polygon and then you just repour it. And now if you look in, all of the ground connections have these little cross hatches on them. Now the reason it's connected like that, it's essentially for thermal relief. So if you're soldering this component, if you have a huge amount of copper around this pad and you're holding the soldering iron on it, it will take a very long time to heat up because it has to heat up all the copper. Whereas if you have smaller connections, it will heat up quicker and therefore the solder will melt quicker.
Sorry, could you go through the pouring process again?
Yep. So polygon pour,
yep,
or polygon plane is the fifth on the right, and then just select each of the four corners. And then so it'll keep going, right? Once you've picked your four, you just hit escape, and then it'll define the square. Then it'll pour, but it'll pour with nothing. Then you've got to use the eyedropper to pick a ground net, and then repour.
Is there a reason to put it on the top layer versus the bottom layer?
You do both. Well, you can do both. So one thing you can do as well, if you don't want to route say all of your components are like 5-volt components and you don't have a mix like we do here, you could do your top plane as a 3.3 volt net and then do your bottom plane as a ground net. That's also fine. You just need to make sure that you'll have to route all of your ground nets to a via so that it can connect to the ground net on the bottom plane.
Sorry, I'm not seeing the little dropper. I might have missed something.
So click the ground plane and go properties.
Yep.
And then there should be net ground and then the eyedropper. And basically, so once you've done that, do exactly the same thing on the bottom layer. Yeah.
Can you link 5-volt traces together? Like, is there any reason that you couldn't just make them all connect at one point, kind of?
Yeah, so you could do like have your 5-volt source in the middle here, and you could branch out like that.
All right. Okay.
I guess like if you've got like a ton of say your 5-volt supply is like here. If you've got like one thin trace and then you've got like, a whole bunch of devices up here all connected through this one thin trace, just keep in mind that all the current for those devices are going to go through this trace.
Yeah.
So you might want to make it a bit thicker if it's doing a lot of current, but in general for small things like this, that it's okay. So yeah, just going to redo the polygon on the bottom layer as well. And then again, don't forget to select your ground plane, your ground net. And the reason you do it on both layers is just as sort of like an EMI thing. It's not like realistically this board would function perfectly fine without a ground plane on the bottom and top. But you might as well get more copper for your dollar. And yeah.
And they're actually manufacturing it. Wouldn't it be cheaper for them then they don't need to etch off copper?
It would be, yeah.
Yeah, if you're going to do that, you also need to stitch it. Via stitch it.
So is there a way to automatically do that?
Yes, there is. I don't know exactly what it is though. I don't put ground planes on the top layer.
Yeah. So if you wanted to instead, we could change this top layer net to be 3.3 volts and then repour it. And now all our 3.3, we wouldn't have to route all those traces for the 3.3 volt nets.
Will it automatically take all the pads that are on your top layer and put vias to get to the ground plane?
No.
So you have to go through.
So you'll have to. Yourself. So if you only have so if you've only got here like this ground net here, this is not connected currently. So you'll need to route to a via. And it's complaining about short circuit because I've routed through this polygon. So I need to repour it. And now it's actually connected. So I'm just going to change it back to be a ground net just to keep things simple. And we've already routed those. So this is routing done. See you, Bashar, no worries. Now the final thing is those design rules that we imported earlier. We need to run a design rule check. And by final thing, I mean, this will probably take you a bit of time to fix. So where is it? Where is it?
Tools, I think.
Oh yeah, tools design rule check, the first one. Thanks, Matt. And if you just run this, basically it'll just go through all of those rules that you defined earlier, and it'll tell you what problems you've got. So we've got 18 rule violations, and I can guarantee almost all of them are because of that weird connector. So it'll put them all in the messages here. And you can see, yeah, so between pad and via, yeah, it's all this thing. So, okay, here's one. Okay, unrouted net. So, this is interesting. Cool. Okay, so what happened here? Yours might not be doing this, but you can see that the ground plane actually didn't get into here. It's because there's no way it can. Because this via is here and these traces run so close to it, the ground plane can't actually connect to this section in here. So both this net and both this pin and this pad of the capacitor are actually unconnected right now. So to fix that, I'm just going to move this via over here, and then repour the top layer and also repour the bottom layer.
But now don't you have that unconnected net?
Yeah, so now the 3.3 volts is a bit annoyed. I'll just do that and repour it again. There we go. Oh, and even still, it's still. Why isn't it? Okay, that's a bit of a bodge fix, but I'll do. So again, run your design rule check, and yep, cool. So now the only errors remaining are this thing, which we don't really have time to fix. And these errors about minimum annular ring. This is part of the component, so we'll have to go into the component editor to fix this problem. It's actually not really a problem. All this is complaining about is that the hole here, there's actually no copper around the hole to solder to. But if you take a look at the part, these holes here, these are just plastic, like mounting holes. So doesn't matter that there's no copper. So yes, GLC will not be able to make copper that's that thin, infinitely thin. But we don't care, and they'll just do what they can. Yeah. Now there's a bit more to this, which I won't go through today, about how you export your files and export your build materials and stuff like that. That can come later, or once you guys are kind of designing boards and getting finished up with that. But yeah, that's sort of everything. Does anyone have any questions or anything?
If I could grab a hand with the port, for some reason
Yes.
it just isn't connecting. Do you want me to share? Because maybe
sure.
I'm just not. I ignore my beautiful routing. But if I just pour. And then properties.
So hit escape again.
Yep. Properties. And then just select one of the grounds.
Yep. And now go properties again.
Yep.
And hit repour right at the very top.
Oh, that's what I was missing.
Yep.
All right.
Now you've got some. What are those green things? What's it complaining about there? Have you?
What has it done? Have I put them on the wrong layer?
No, it's just complaining because that connector's outside the room. So if you just delete your rooms, it'll.
Ah, right. Yeah.
It's a bit weird.
Can you hide pores?
Yeah. So if you click on it and just click the pore and go properties, and then if you shelve it, it will at the top. It'll kind of hide it.
Oh, cool. What was the issue? Just the
so that J3 connector is outside of the room. So if you just and so you just delete all your rooms, it'll nice. So and now to unshelve unshelve pore. Don't be afraid to Google stuff. There's fairly good resources. So if you go tools, polygon pores, which is like 5th or 6th from the top, and then restore.
Oh.
And then you might have to re-pour it.
Yeah, it looks like it.
Yeah.
All right, awesome. Cheers.
Nice.
Is there any way for your PCB, say I accidentally zoomed out too far, is there any way to center it in the middle of the screen again?
I did the same thing. It was like struggling.
Yeah, I lost
it. So usually that's because, hang on, I'll show you. So if you like have your wire tool, right, and you hit escape, and then you like go like Alt Tab into something, and like move your mouse to the side of the screen, it'll just start panning to the right. And so now I'm like, so you can like zoom out as far as you can. That's one way. I think
there's an option in view to center it.
View
fit document, I think. Fit board.
Oh yeah. There you go. Fit board. Nice. Thanks.
Hell yeah, thank you.
Cool. So yeah, that's the process basically. I've taught you how to use the tool. I can't teach you how to design electrical systems, unfortunately, but that will come with time and practice. Stuff like this is going to be a fairly common like sort of systems where we use a PIC and some sort of chip and communicate over CAN. This is going to be a recurring theme for the next design cycle. If you want to have a look, I guess while I've got you here, I can show you sort of what other people are working on. So like Matt's working on. So this is the battery board. So this is what Matt's working on. So you can see there's a PIC here, and we're using a lot of extra features with the PIC for like cell balancing and stuff. And yeah, there's a fair bit going on. But
what are all the numbers?
So these are comments. So you can see Christos has added a comment here. These are quite helpful because you can list them all. So if you go panels, comments, you can see all the comments here. So we sort of use this as a method of debugging. When we do reviews, everyone just leaves a slew of comments on every schematic, and then you can kind of go through and address them as you go. Or if there's any notes, like for example, when we were doing the carrier board, I would go through and add comments on parts that weren't available at element 14, and then I would just have all those comments, and then I'd come back through later and find replacements. And just because I can, I'll show you some of the Jetson carrier stuff. So this is the top sheet for the Jetson carrier. It's an absolute nightmare. Don't worry if you don't understand what's going on. And like, so for example, we have this. So this is like the connector for the Jetson module. So there's 400 pins. So because we don't want to like look at this and have to run wires all around this, we just broke them all out into ports, and then we have this big tall subsheet here is just a representation, so we can group all of the relevant pins together. And then like if you want like HDMI, this is what HDMI looks like if you're keen. And then the PCB, when it loads, is even scarier. but yeah, don't worry. This is not something you'll be expected to do anytime soon. I've been designing PCBs for like 2 years. And even then I don't really know what I'm doing. So this is what a nightmare looks like. But in principle, it's all exactly the same thing. There's just a lot more connections. So instead of having 10 components, we have like 300. And yeah, so one thing I've done, so like this is the HDMI circuit, for example. So you can see these are, Isaac was mentioning before, the differential pairs. So you've got to route these very carefully and make sure they're sort of the same length. And so one thing when you're doing a board of this scale is with connections, I hide them all. And then I just go through and like turn on the connections for components I want to do. So there's also view connections, show component nets, and then you can turn on just the nets for specific components. So if you just want to like route a specific area. And yeah, that's what the 3D view looks like. So you can also add logos. There's a thing on Nuclino on how to do that if you can. And I put a big one on the back. Yeah, that's it basically. Any final questions or anything?
When you have more than 2 level of schematic sheet, like you have nested one, how do you order it? Yeah, for the system.
Yep. So it's exactly the same basically. Nothing really changes.
I think it's for one more level.
Yeah. So this is the top. This is the top sheet, and then for example, we've got the USB block here. So all of the USB connections go to here, and then here we break them out into the individual connections. So we've got, this is a good example of a repeated connector. So we've got 2 USB 3 connectors here, and they both run to different sets of USB lines on the Jetson carrier. And then yeah, they go there's quite a few layers here, but so this is like the connector. And then just to like neaten the schematic up a little bit, I have this power switch circuit here with just the enable and the output lines.
Right, yeah.
So you can go as many layers deep as you want. It's sort of a trade-off between like neatness and readability. Too many layers deep, you can sort of lose track of what's going on. But not enough layers, and the schematic can just be absolutely overwhelming to look at. So yeah, sort of there's an art to designing schematics and PCBs that's that you'll kind of get with practice.
Do we have an Arduino Nano in our components library, or?
I don't think so.
What have you guys been using?
We haven't designed an Arduino board in Altium yet.
Oh,
so like if I search, I don't think there'll be anything in the manufacturing part search.
No, I looked, there's like one, but it's not right.
Yeah, it's the IoT one. You can make one if you want to. We're trying to move away from Arduinos, but if we do an Arduino board, we'll just make a footprint. If you guys want to stick around, I can show you how to do that. That might be a good example.
Yes,
but if you need to go, feel free. And if you're not interested, feel free. But making components is quite important. So
definitely.
Yeah, so okay, I might as well. So if I search Arduino Nano, it doesn't exist. So I can go create component. I'll probably just show you how to do this, because if you all create one, we'll end up with like 15 Arduino Nanos in our library. So you kind of got to pick a category. We can make some more categories. I'll just put it in undefined for now. All right. So first off, we need to give it a name. So let's call it Arduino Nano. And then we need to make a symbol and a footprint. So the symbol we'll use the wizard, because the wizard is helpful for this. And let me just pull up what a nano is like. All right. Grab a screenshot. Did that not work? Yeah. Where's my thing? Okay, whatever. So all right, so we've got 30 pins, so we'll go number of pins 30. And then dual inline is fine. So yeah, with the wizard, you basically just have to go through. So there's position, which is, I don't know what position is actually, and then display name. So we'll go through and like D1/TX, D0/RX, reset ground, D2, D3, D4, D5. You can do all of this in a spreadsheet and then like copy the spreadsheet into this. Oh wait, let's fix that. Yeah, so there is, yeah, Min's right. You can like import stuff as well.
Yeah, there should be. It's pretty popular bot, but yeah, just make sure to double check all the pins and footprint and stuff.
Yeah. So and then the main thing you've got to check is these inputs. So so like V in would be power. I'll change them all. Anyway, I'm just gonna change them all to be passive. Oops, where'd that go? All right. And there we go. So now we've got this, so that the wizard just does it for you, which is really handy. And now, so that symbol's done. And now we need to make a footprint. The wizard for the footprint is only very good for like certain types of footprints, which this isn't one of them. So I'll have to make a new one by hand. And this is very similar to the schematic stuff. Sorry, to the PCB stuff. Let's see if I can find the dimensions. Okay. Yeah, cool. So in general, pins like this are 2.54 millimeters apart. So we're going to want to go, so this tool here is pad. And right now we've got a square pad, which is not what we want. So you can change it to shape round. And then how big should these be? Christos, what's off the top of your head? I can't remember.
For an Arduino Nano, 0.1
whole size.
Oh, 1 millimeter, sorry.
And then like, oh, they go with 2 mils.
You might have to make it a little smaller than that. The pitch is 2.54. Actually, no, 2 is probably, maybe do like 1.8.
We'll go 1.5, that'll do. All right, also my thing's in mils, which is really annoying me. So if you remember to change the units, you just click on like anywhere and go to properties, and then down the very bottom.
I believe Q is also the hotkey for that.
Oh, there you go. There's a hotkey for everything.
Indeed.
Now, a little trick of the trade. Because the pitch of these connectors is 2.54 millimeters, I'm going to change my grid size to be 2.54. And then I'm going to change that to be pin 1. So we go, pin 1 is here down to 12, and then 13, Yeah, so we're down to 15 actually. So if I copy that, all right, and I need to change all these designators to be the right pin number. So you can just double click and it'll automatically start on the designator like section. No worries, Isaac. See ya.
See ya.
All right, so that's up to 12, and then I need 3 more. So 13, 14, oops, 15. Okay, so now I've got all the pins there. So that's one side. And what's the gap between the sides? That's a good one, 15.24. So I'll copy this. And then if you need to measure, Control M is the measure tool. So you can, and nice, I got it exactly right. So 15.24 between center to center. And now I need to go through and change all these as well. So 16, 17. Come on. All right, cool. So that's done. So that's just the pins. In principle, this is all you technically need to do. But it's definitely worth adding a little bit of extra detail to help you with layout and all that. Oops. So for example, let's add a box around it on the silk screen. So silk screen is top overlay layer. And you can go right, if you right click on the line, you'll get the rectangle tool. I'll just start with something like that. And then I can measure, so that's 40.64, which is correct. Oops, and okay, so I've lost my thing, there it is. And then the width is 20.32, which I don't think is right. Where is that? It should be 17.77. So I'm going to pull that in. I'm going to make my grid 1 point. What's half? 1.27. And then if you got, I can't remember how to clear the measurements. Anyway.
Shift M, I think. No, not that.
Oh, you can Google it for me and I'll do it in a sec. Now that's 17.78, which is, yeah, that's correct. Cool. So we've got like an outline of where the Arduino actually sits on the board. And I'll probably also add just an outline of like which way the Arduino goes, because it can very easily be modeled up. So if you have a look, pin 1 is right at the back. So I'm going to put a rectangle kind of here, and I'll put some like text in there for USB.
Shift C, Will.
Shift C. Thanks, Matt. So that makes it clear to people that this is the orientation of the Arduino. So when they put it in, they don't put it in backwards and blow it up. You can also so you can also add a 3D model for it. I don't have a 3D model handy, so I won't show you exactly how, but this tool here, place 3D body, and then you can import a step file. I'll just show you like with the Jetson module. Actually, that might have been a mistake because it's quite big. Let's see what happens. Maybe. Hello.
Did you just download that step file from like GrabCAD or like someone else?
It was from the NVIDIA website, yeah. So you can chuck in a 3D model. The pink like hatched box is the 3D model, and it's on mechanical 1 layer. I guess just a general note, not all of these layers actually correspond to a physical PCB layer. There's often extra ones that aren't used for anything. But I'll get rid of that because it's not
funky looking Arduino.
Yeah, damn, it's a big Arduino. Cool. So then you save that and you hit save to server. Now when you try and save to server, it'll tell you if there's any issues. So we haven't specified a type or a description. I don't care. It'll do.
Don't you need the description for when you're searching?
Possibly. I guess we'll find out. That's there. So now, if I wanted to add an Arduino, we now have an Arduino.
Nice, thank you. How important is it that the like the holes in the, not that one, the
footprint?
I'm not sure what to call it.
In the footprint?
Footprint?
Yeah. What was your question?
Oh, sorry, I think I cut out. How like important is it that they're the right size and distance apart? Like pretty important, yeah.
Incredibly important. If it's not correct, the component won't fit.
Yeah, distance apart is super important, and size, it has to be bigger than the pins or they won't physically fit.
Yeah.
But once you're over that, there's a fair bit of tolerance, like how tight do you want to have it to the pin? And how wide you actually want the copper on the pad. Both of those affect how easy it is to solder or how easy it is to bridge them.
Right. Because you guys you don't solder Arduinos directly to the board. You use those things that you
We use headers, yeah.
Headers,
yeah.
Thanks. Yeah.
Yeah. But headers are the same pitch and everything.
Yeah. Cool.
And it's impossible to desolder an Arduino once you solder it on if you don't use that.
Yeah,
stuff.
no.
Yeah.
I was gonna say. So are those dimensions correct or should
I think what I've got is right. Yeah.
Yeah, cool.
But yeah, always treat footprints that are not official with skepticism.
Okay.
I guess I'll quickly show you as well. If you want to, say like we didn't have a footprint for this tantalum capacitor from back at the start. You can often, on Octopart, often they have all the files for you. Sometimes you might need to go elsewhere depending on the manufacturer. But here there's, for this component, there's an Altium designer file, and it'll give you this zip file. If you open it up, it'll have the PCB library, the schematic library, and the step file. So what you can do, I'll just like chuck these on my desktop for now. So if you drag this schematic library into the right pane, you can see it's here. So you can just open this up, and obviously it's a capacitor, so the schematic is just like a capacitor symbol, so that's easy. But the PCB library will be more complex. So it opens that up. So now that you've got these here, when you're making so you put your part number in, you go create component, you can just, there's probably a way of actually like importing these as the actual thing. The easiest way that we found to do it is just to copy the whole thing, and then go to your new footprint and schematic and paste that there. But yeah, so I guess if you're looking for a footprint, first just Google if there's some available. There's sites like SnapEDA, and like Ultra Librarian are a couple. They have some like pre-provided footprints and schematics and 3D models, but you might need to make your own if you can't find any. Anywho, I think they'll probably do.
I've got one more question.
Yeah, go.
Sorry. About the ground plane.
Yep.
Christos, you mentioned that you tend to not put a ground plane on both layers. So like, what do you do with the rest of the space on the other layer?
Nothing.
You just leave it.
I just leave
in a
it.
copper.
Yeah, but it kind of depends. So if you have a very sparse board, it can be kind of nice to have copper there. Just I don't know, just so they don't have to remove as much. But honestly, fuck them. Like you do whatever you want. But if you do a pour like that, it's very important that you ground it. Like you connect the two layers. So what you do is something called via stitching, which is where you basically add a big grid of vias that link the two together. And that means they have to drill more holes. So it actually makes more work for them than it would probably be just to remove the copper.
Yeah, so you
can't just put one via to connect them.
No, you want to have lots of them. Otherwise, they're not very well coupled.
Yeah, so I guess the thing with PCB design in practice is that like, although everything's like two things that are the same net, in principle, in theory are the same voltage, but in practice they're not, because any slight current through that, because the traces have resistance, will change the resistance. Oh, sorry, change the voltage. And yeah, so if you're like for this sort of thing, it'd be fine. But if you're doing stuff that's precise or you like, it's good practice to kind of make sure everything's grounded properly.
Yeah. And yeah, a lot of the times if you're making relatively dense boards, like you're space constrained, the boards will be so dense. If you do a top pour, it'll just be kind of sitting in the corners and not doing much anyway.
Yeah.
If you do a top pour, don't let it'll now connect all the grounds together, but really you want to make sure you still have a via right next to all the pads that are actually connecting the ground going to your ground plane. And then once you do that, you don't actually get much benefit from having the ground pour on the top plane. So that's why I don't generally do it, but it's something that's very much up for debate.
Yeah,
I know a lot of people that do like to do it. So
in general, with like ground planes as well, you sort of want to avoid cutting your ground plane with traces like we have here. It's not as important for like low speed stuff like we're doing in this example, but for example, if you had like a very high speed like USB line that ran on the top layer across these directly, because USB is really high speed, not only is the voltage changing very quickly, but with voltage comes current changes very quickly. So in order to have and when you have current changing, you get like electromagnetic induction. So what you want to do is you want to have the ground return path for your USB lines to be exactly underneath the trace to cancel out that induction. But if you've got these traces running across here, the ground return will have to go around this through the ground plane. So yeah, just something that you won't need to worry about until you're designing more complex boards. But just might be interesting.
Yeah, the most grievous thing. So you basically you can have things in the ground plane, but you want them to be as short as possible. So like, see the little one that we've got in sort of the middle on the left, that's great. Perfect. Do stuff like that. But some of these big long ones, if you actually care about the integrity of your ground plane, let's say that one on the left there, you'd use the ground plane to go under what you need to, but then pop it back up onto the top plane as soon as you can.
Yeah. In fact,
that way it's as short as possible, because you have like a little hole in the ground plane, signals will go around it, it'll average out, it won't really notice. If you have a big slice through it, then your return path now is so much longer than your other path that you'll get EMI problems and stuff.
And yeah, in principle, we actually don't even need the bias here. But that's fine. Anywho, cool. Well, probably wrap it up there. I'll stop the recording. Actually, Christos, can you stop recording?